Before we explain what a distributed system actually is, let's define a fundamental age-old problem that pervades not only computer science and blockchain technology, but all of humanity. How does a group make a decision? Whether this be by majority opinion, general agreement, or force, how do we achieve consensus? Consensus is trivial when we only have one actor. I can always agree with myself on where to have lunch. But when I go out with my friends, we all have to agree on where to go first, and the process by which we reach agreement might be difficult. In this example, my group of friends has come to consensus on a common choice of action, what to get for lunch, before we were actually able to move forward with what to actually get for lunch. This is no different from how a distributed system actually works, and it is from here where we start building our intuition and context. Consensus has been studied for ages in fields such as biophysics, ethics, and philosophy, but the formal study of consensus in computer science didn't start until the late 70s and 80s, when people decided that it would be a good idea to put computers on airplanes. The airline industry wanted computers to be able to assist in flying and monitoring aircraft systems. This included monitoring altitude, speed, and fuel, as well as processes such as fly-by-wire and autopilot later on. This was a huge challenge because being at such high altitude poses many threats to normal execution of computer programs. For one, it's a very adversarial environment. Being so high up means that the atmosphere is thinner, increasing the chance of a bit flip due to solar radiation. And all it takes is a single bit flip to completely destroy the normal execution of, for example, the sensor measuring the amount of fuel an aircraft has. Compounded on this was the fact that aircraft could cost hundreds of millions of US dollars, in that commercial airliners where these computers were going to be deployed could carry hundreds of passengers. So, super dependable computer systems were first pioneered by aircraft manufacturers. They realized that the problem they were solving could be solved by introducing redundancy in their system. Instead of using a single computer on board their aircraft, thus having a single point of failure, they used multiple computers on board to distribute the points of failure. How these computers coordinated amongst each other, though, was another challenge. Early literature had focused on enabling coordination of processes, where these processes could be processes on a CPU or computers in a network, separated spatially. One of the most impactful pieces of literature during this time was Time Clocks and the Ordering of Events in a Distributed System, written by the computer scientist and mathematician Leslie Lamport in the late 70s. In Time Clocks and an Ordering of Events in a Distributed System, Lamport showed that two events occurring in separate physical times can be concurrent, so long as they don't affect one another. Much of the paper is spent defining causality, what it means for an event to happen before another, in both the logical and physical sense. This is important because determining the order of when events take place, such as the measurement of a sensor or detection of error and subsequent error correction, as well as determining which events actually took place in the first place, is crucial to the correct functioning of a distributed system. On the right, you can see one of Lamport's diagrams depicting three processes, the vertical lines, each with their own set of events, the points on these lines. Time flows in the upwards direction, and each squiggly line between events represents a message being sent and received at a later time. If there exists a path from one event to another, by only traveling upwards in the diagram, then that means that one event happened before the other. If an event doesn't happen either before or after another event, then it's said that those events are concurrent. For those of you with experience in quantum physics, you may notice the resemblance between Lamport's diagrams and Feynman diagrams, which show the interaction of subatomic particles. Lamport realized that the notion of causality in distributed systems was analogous to that in special relativity. In both, there are no notions of total ordering of events. Events may appear to happen at different times to different observers, in the case of special relativity, or processes in the case of distributed systems. While this is at a depth that's out of scope for this course, it's important to recognize that through the efforts of Lamport and other scientists, the formal study of distributed systems began to take shape. And as it turns out, the same problem that was originally studied to coordinate computers on commercial airliners is still studied today, for example, on more high-tech jet planes. and more recently on various spacecraft, such as SpaceX's famous Falcon 9 or Dragon spacecraft. For example, spacecraft have to be tolerant of violent vibrations when accelerating through Earth's atmosphere, and when they do leave the atmosphere, they have to deal with the intense heat and cold depending on which side of Earth they're on, and also solar radiation. SpaceX Dragon specifically uses 3 flight computers which perform calculations independently and reboot automatically if errors are found after cross-checking. Distributed systems and consensus is also studied in the context of big enterprise operations too. Distributed log servers, for example, ensure that no 2 processes can read or write to the same piece of data at the same time, a problem called mutual exclusion, thereby preventing potential corruption to important data. And finally, of course, the main focus of this course, the blockchain and distributed ledger revolution. Fundamentally, each of these problems we just went over, and more, reduce to the problem of consensus. In aircraft like rockets, jet planes, and commercial airlines, a number of redundant onboard computers must come to consensus on sensory data, for example, the position of aircraft, its location and altitude, as well as its fuel levels. In enterprise distributed log servers, processes must come to consensus on who can write to what data at what time, as the coordination of this prevents data loss and corruption. And finally, in blockchain, full nodes agree on some state of the system, depending on implementation. In Bitcoin, users agree on who owns what in Bitcoin, and in Ethereum, users agree on the correct execution of transactions and the general state of the Ethereum network. Consensus attempts to create a reliable system from potentially unreliable parts. Parts like the computers in aircraft that are vulnerable to bit flips due to radiation, or maybe a power outage in a data center. Or in public blockchains, for example, where the ever-changing network topology, as well as the existence of malicious entities trying to subvert the entire network for economic gain, for example, don't align with the goals of the system as a whole. Instead of trusting the execution of individual processes or reliability of any individuals, we trust the general protocol and the math behind it. It's trust without trust.